All right, there we go. I think we have it recording now. So welcome everybody to lecture 5, S25. Today we're going to be doing the first of a two-part lecture on kind of a crash course in orbital mechanics or spaceflight mechanics. And this is going to be, hopefully this will make sense with kind of a metaphor. There's a lot of really, really interesting and useful topics in orbital mechanics, and we're going to cover very little of it. It's going to be a very narrow slice, but it's going to be the parts that I think are the most useful to a spacecraft navigate. Ordinarily, I like to start these lectures with like a rhetorical question, or like it make more sense. I think for now, I'll just draw you like a little picture. But the idea that I want to get across is, among other things, is if you have the Earth, I'll take the time to actually draw this in the right color. If you have some central massive body, and you know the coordinate frame that you're operating in, and then let's say that you've got some spacecraft, and you know, oops, there we go. And you know it has some position, and you know it has some velocity. The point that I want to make is that that position and that velocity can be used to extrapolate so much, because you can actually go through, you know what, I can do slightly better than that, trying to like make an orbit. From a position and a velocity, there is enough information to kind of infer the rest of the trajectory, unless some external force acts on the spacecraft, if that makes sense. So the state of a spacecraft, and in this case, I mean position and velocity. We won't be talking about attitude in this section. Has enough information to propagate into the future if you have the right tools. And so for the next couple of classes, we're going to talk about what those tools are. And so I like to think of it as knowing the full state of a vehicle at some time is kind of like a seed. You know, if you plant an acorn in the ground, you get a tree that grows from it. In some very real way, the whole tree was inside the acorn the whole time, right? It's almost like a compressed, like a zip file. It's compressed in there, and it needs, you know, sunlight, and it needs water, and it needs nutrients. But the whole tree, the information to construct the whole tree is in the seed. The information to construct the entire trajectory of a spacecraft is in its state. And I want to make that make sense over the course of the next two lectures. So if I was to give you position and velocity, you could give me the position and velocity at not only some future time, but any future time. And then you could use that to say, like, propagate an entire orbit. We use this in navigation, but it's also useful, you know, for other applications. And this is going to come up on homework 1, where homework 1 is going to be a lot of, here's the spacecraft at one time, here's the state, what is its state at some future time, and demonstrating that you can do that using multiple different techniques. So this is a review of orbital mechanics. And today, we are going to go over the two-body problem, or two-body equations of motion. It's equation singular of motion. And then we're going to go over a derivation of eccentricity and angular momentum. Then we're going to go over just some miscellaneous useful equations that have to do with orbits. And then we'll take a break. And then we're going to talk about Kepler's equations, and some examples. of how to use Kepler's equations. And that's today. And then next class, we'll go over the parafocal reference frame, orbit elements, and do some examples, converting position and velocity to orbit elements, as well as just kind of a primer on everything else that you'll need to know for homework 1. Homework 1 is also going to touch very briefly on some topics from the next kind of section after these 2 lectures, which is orbit determination problems. But that's going to be kind of minimal. So definitely after this lecture and the next lecture, you'll be pretty well equipped to do homework 1. So next is the 2-body problem. All right, so we're going to start with Newton's second law. So I'm wondering if anybody knows or remembers Newton's second law. I'll wait and see if somebody brave wants to key in their mic.
M equals F equals
The F equals ma, but we can be a little bit fancier than that. All right, let's say we're talking about a particular particle. So we'll call that particle P. Is it just F, or is there something else? Like, is there one force or are there many forces?
F net.
Yep, F net. Or I like to think of it just as the sum of all the forces, and these forces are vectors, acting on some point P, is equal to the mass of point P, and this is true for a point mass or for a larger body, times the linear, this is linear, acceleration of P, this is vector superscript, and then top right is the point P, top left means in some Newtonian reference frame. You could also call that some inertial reference frame. I use those interchangeably. So you could swap that N for an I. So there's Newton's second law. From that, I mean, pretty much most of what we do as like mechanical and aerospace engineers have something to do with Newton's second law. So from here, I'm going to say, okay, let's say that we've got some reference frame, some Newtonian reference frame, where here's the N1 direction, here's the N2 direction, here's the N3 direction, and let's say that there is some relatively large massive body here, and then there is some much smaller massive body over here. There we go. And I'm going to call this vector here capital R1. I'm going to call this vector here capital R2. And then on this dotted line between the two of them, there is some point which is their combined center of mass. So hopefully you're familiar with like the little center of mass logo here. That's my best effort at drawing it. So this is the center of mass of point 1, which has mass 1, and point 2, which has mass 2. We're going to call the center of mass S star. Okay. So hopefully this all makes sense. Oh, and then point 1 has mass 1, point 2 has mass 2. Okay, there's our system. Looks a little spooky, but all it is just 2 points floating in space. They both have some position, they both have some mass, and the weighted sum of their masses is the point S star, the center of mass. So let's formalize that first thing. The vector R, which points from the origin, so maybe the origin down here is point O, the vector R to the center of mass S star is, we just said it's the weighted average of the masses of the two bodies, right? So it is the vector to point 1 times the mass of point 1 plus the vector to point 2 times the mass of point 2, and then we divide that by the total mass, m1 plus m2. So this gives us our center of mass. Hopefully that makes sense. Okay, now what we're going to do is we're immediately going to throw out the old reference system, and we're going to introduce a new reference system where we move the origin to the center of mass. So things are actually going to get a lot simpler, because pretty soon we're only going to have to work in 1 dimension instead of 3 dimensions. So we're going to move our origin to our center of mass. Okay? And so you can think of it this way. Here is point 1, here is point 2, here is the center of mass. I'm going to try again to draw a good center of mass icon. Here we go. And let's say that this vector here from the center of mass to point 1 is little r1. This vector here from the center of mass to point 2 is little r2. And then this vector here, and I'm going to draw this in parallel, but hopefully you get the idea. The vector from point 1 to point 2, we're just going to call r. And maybe the fact that we're using a relatively simple term for r makes you think that, yeah, we're going to use the vector from point 1 to point 2 quite a bit in the equations to come. And you'd be right about that. So under this system, r is negative r1 plus r2. And then if we wanted to get fancy with it, r dot, the derivative, is negative r1 dot plus r2 dot. And then r double dot is negative r1 double dot plus r2 double dot. Hopefully that makes sense, just taking some derivatives. Okay, but now we can say, okay, what is the relationship? What are the force that's acting on each of these points? So the force of gravity, using Newton's law, acting on point 1, this is a vector, is what? Okay. Well, it's going to be g mass of 1, mass of 2, okay? And then it's going to be r over r cubed negative, and that is equal to the mass of 1 multiplied by r1 double dot. So let's think about that for a little bit. The force of gravity of point 2 acting on point 1 is mass times acceleration of point 1. And this is g m1 m2 r over r cubed. The r is the distance, because it's not the center of mass acting on point 1, it is point 2 acting on point 1. Okay, and then the negative is saying that it's pulling it in the negative direction. I'm sorry, actually, positive. Whoops, that should be positive. Okay, the next one is negative. So the force of gravity acting on point 2, well, this is the gravitational force applied by point 1. So this is going to be gravitational constant, m1, m2, r over r cubed. This is negative, right, because we're pulling it in the opposite direction. And then this is equal to the mass of 2 times r2 double dot. Okay, so far so good, I hope. We're in good shape. We're going to go through and combine this equation here with these equations here. And what we're ultimately looking for is some equation that lets us describe the position of the smaller particle, P2, which is the one that we're more interested in. Maybe you might kind of be able to guess by now that the larger one is analogous to a planet and the smaller one is analogous to a spacecraft, but spoiler alert. What we'd really like is some equation that lets us describe the position of the smaller particle and relate that to the derivative, in this case, the second derivative of this position. So this would be an equation of motion that allows us to propagate forward in time. So just wanted to take a checkpoint here, make sure that makes sense. Now, before we do that, we're going to do some manipulation here. I'm going to call this equation 1. I'm going to call this equation 2. Now, equation 1, if you take g m1 m2 r over r cubed is equal to m1 r1 double dot. What I'd like to do is multiply both sides of this equation by m2. So there's an m2. This would get m2 squared. Okay? And then what I'd also like to do is take equation 2. And equation 2 would be negative g, maybe you see where we're going with this. We're going to multiply both sides by m1. So this is going to become m1 squared m2 r over the norm of r cubed. And that is equal to m1 m2 r2 double dot. Okay, so far so good. Now we can finally combine these equations. So if you combine equation 1 and equation 2, what do we get? In this case, it's going to be g m1 m2 squared r over r cubed minus g m1 squared m2 times r over the norm of r cubed is equal to m1 m2 r1 double dot plus r2 double dot. But now we want to be careful. We really want the right side of the equation to say negative r1 double dot. So actually what I'm going to do is I'm going to take negative equation 1 plus equation 2. So this term becomes negative, this term is still negative, this term becomes negative, this term is positive. Okay? And now negative r1 double dot plus r2, well, that is just r double dot. All right? So our algebra tricks are largely over. Now we just need to simplify. So this becomes negative g m1 plus m2 times m1 times m2 r over the norm of r cubed. And this is equal to m1 m2 r double dot. So cancel, 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 cancel. Okay. And next we're gonna introduce a new term. We're gonna say, okay, g m1 plus m2 is approximately equal to gm1. So this is assuming that m1 is much, much greater than m2, like orders of magnitude larger than m2. We're going to assume that the mass of the second particle is negligible. And then we're going to define that gm1 is called mu. Mu is the gravitational parameter. It could be the gravitational parameter of the Earth, but it's the gravitational parameter associated with a massive body floating in space. Okay. And this triangle on top means is defined as. So we are introducing mu as some new character, which is just gm1. Okay, so after making some approximations, we can say that negative mu r over the norm of r cubed is r double dot. And this features a couple of approximations. But first, I want to pause and celebrate. We have an answer. And this is our two-body equation of motion. So really quick, I want to hear what are some assumptions that went into getting this result. One of them is a freebie. We just talked about it.
M1 is much, much larger than M2.
Yep, absolutely. But now imagine you've got a spacecraft orbiting the Earth. Is this a good approximation of the physics governing a spacecraft orbiting the Earth? Or are there some other assumptions kind of baked into this math problem?
R is constant. Well, no, R doesn't have to be constant.
No, R doesn't need to be constant, but what about all the other spacecraft orbiting Earth? Like, would those have some gravitational impact? Like, I guess so, probably negligible. So you can probably safely ignore those. But what about the moon? Does the moon have a negligible impact on the orbit of a spacecraft? Depends, right? Depends on over what time period. If you propagate the two-body orbit of a spacecraft and then you propagate, the actual like tracked position of a spacecraft, you'll find that they diverge after a while because there's physics happening in real life that we haven't captured here, right? So we're assuming that there's no other bodies at play, like the moon or the sun, or even Jupiter can have some detectable impact depending on the trajectory of your vehicle. And then also, we've assumed that we're in an inertial frame. And the Earth-centered inertial frame, despite the title, is not actually inertial. So I want to mention that this is a extremely useful equation, but it is ultimately just a mathematical model. It's not capturing everything that's going on. But what we can do with this is we can take the position of a spacecraft at some time, and we can compute its acceleration, which is extremely useful. And we're going to see this on homework 1. If you can compute its acceleration, you can determine it. So essentially, if you've got the position and the velocity at some time, you can use this equation to say, okay, well, here's how the velocity is going to change over time. The velocity is how the position is going to change over time. And you can march forward using something like, ordinary differential equation solver, which is ultimately based on like a Taylor series expansion. You can take the equations of motion to march forward in time and propagate to some future state, which I think is pretty nifty. So any questions on the two-body equation of motion, or are we good to proceed? All right, good stuff. Next up, we're going to talk about angular momentum. This is going to be a nice short little topic here. Angular momentum. Okay, so we're going to define some term. So let's say that we've got some massive body and it's got some reference frame that works like this. And let's say that you've got an orbiting spacecraft. Spacecraft's out here. And it's got some position R. It's got some velocity V. Then it also has some H, where H is your angular momentum, and it is defined as R crossed V. And so the idea here is that R and V are in the kind of XY plane, and then H is perpendicular to both of those. I hope that makes sense from the diagram. Specifically, oh, sorry for the play on words, this is specific angular momentum. Because you'll notice that mass does not feature in here. This is specific angular momentum. Now, some of you may be familiar with the law of conservation of momentum or the law of conservation of angular momentum. If angular momentum were conserved, wouldn't it stand to reason that the derivative of angular momentum is 0 for a system in a two-body orbit? I would say probably so, but let's prove that to ourselves. Now, we need to be very careful here, right? We want to take the derivative of h. Now, the derivative of h is not the derivative of r crossed with the derivative of v, right? We need to go through and be careful to use not only our calculus knowledge, but our physics knowledge. So first of all, I'm going to say the derivative of h in some Newtonian frame, right? Not the derivative with respect to some moving frame, right? Because Newton's laws are actually only valid with respect to a Newtonian or inertial reference frame. Things start to fall apart if you're not in a Newtonian frame. The derivative of h is equal to, well, it's not going to be derivative of r cross the derivative of v. It's going to be the derivative of r crossed with v plus r crossed with the derivative of v, right? So you might have learned in calculus 1d2 plus 2d1. That's basically the idea that we're going for here. So this is the product rule. Okay, great. So now, what is the derivative of r? Well, the derivative of r is velocity. So this is velocity crossed with velocity. And then what we get here is r crossed with acceleration. Or I guess we'll call this r double dot. Apologies for the sloppiness, because now I'm using my own, we're using v for the first derivative of r, but then we're using r double dot for the second derivative of r. I know that's poor form, but we do that for a reason. V crossed with v is 0, right? So really, this is r crossed with r double dot. But isn't r double dot, according to the two-body equations of motion, negative mu r over r cubed? So really, this is negative r crossed with mu over r cubed r. Now, this is a scaling term. Really, this is negative r crossed r. And r crossed r is, again, 0. Therefore, h dot is equal to 0 if and only if the two-body problem holds. So hopefully that makes some sense. Now, you see the issue here. We've assumed a Newtonian reference frame, which is wrong. And we've also assumed that this is a two-body system. And there's really no such thing as a two-body system in nature. So the conservation of angular momentum is a nifty trick that we can use, but it is ultimately a mathematical model, and it does not describe real life. It does a decent job for a reasonable period of time. All right, now we're going to be able to use tricks like this in our next derivation here, but questions on our angular momentum discussion? All right. So we're going to describe something which you may have heard of before called eccentricity. Okay. Now, as a shorthand in this derivation, just to make things a little bit simpler, I'm going to say that just the letter r is the norm of r, just to make things a little bit simpler. You've probably seen notation like that before. What we're going to show you is that there is a mathematical construct that just kind of pops out of the two-body equations of motion, which you can construct from position and velocity, which is called eccentricity. You might be familiar with eccentricity as, it's some number that describes the shape of the orbit, which is true, and that the number of the eccentricity has to do with how elliptical versus how circular the orbit is. That is also true. But eccentricity is even more useful than that. It's one of the more useful concepts in orbital mechanics. So we're going to start with the two-body equations of motion, and then we're just going to notice that something really cool just drops out of them. So starting with r double dot is equal to negative mu r over r cubed. Okay. What happens if we cross product both of these sides with h? So r double dot cross h is equal to negative mu over r cubed r crossed h. Okay? Well, let's look at the left-hand side for a moment. So we're going to split this up. Right? R double dot crossed with h. Well, if you just look at the derivative in a Newtonian frame of r dot crossed with h, well, that's going to be equal to r double dot crossed with h plus r cross h dot. But we just said that h dot is 0. Right? So really, you could say that the derivative of r dot crossed h dot is, the derivative of r dot crossed h is equal to r double dot crossed with h. So we're going to make a substitution. This left-hand side is now r dot crossed with h, whole thing, derivative. Okay. Now, the right-hand side, what we get is, and I'm just going to be sloppy for a second here, let's see, how do I want to do this? Okay, we're going to drop mu for a second, and we're going to drop the negative sign for a second. We're going to go over here. R over r cubed crossed with h is equal to 1 over r cubed r crossed. Remember, h is r crossed v. Now, whenever you see triple cross products, you might be thinking of back cab. Maybe you're familiar with that. So remember that A crossed B crossed C is B A dot C minus C A dot B. Back cab. Maybe you're familiar with that trick of cross products. So if we do this, then R over R cubed crossed with H becomes R vector R dot V minus V vector R dot R. And then this is, let's see, R cubed. Okay, and now we can actually go through and let's see, just checking my notes here. B and then B crossed R. Okay, yep. So after some simplification, there we go, we're going to reintroduce mu. So remember there's a negative sign over here. We're going to say, okay, negative mu r over r cubed crossed with h, so this is the left-hand side again, is equal to positive mu over r squared negative v norm of v times vector r plus norm of r times vector v. All right, that's what we're saying. So this is after a little bit of simplification. So finally, we can bring this all back together. Actually, I should mention that this r and then norm of v, v and then norm of r, this is simply the derivative of mu r over r. If you carry out the product rule, low derivative high minus high derivative low over low squared, you get this, right? So we can make a few more simplifications. This term here is the right-hand side of this original equation. And then this term here is the left-hand side of this original equation. So we're going to set them equal. So here we have d dt in n r dot cross h is equal to d dt in n mu r over r. All right. Now, is it safe to just do away with the derivative of both of those? No, because then you need to start thinking about like constants of integration. But what we can do is we can say, okay, the derivative in n of r dot crossed h minus mu r over r 0, which means that r dot crossed h minus mu r over r is some constant value. Right? We don't necessarily know what that value is, but we know it's constant because its derivative equals 0. And actually, whatever that constant value is, we are going to define it as some term c, and c is a vector. Okay? But now it stands to reason that if c is a constant, then c over mu is also constant. This is where it gets really fun. Velocity crossed with h over mu minus r over r is some constant, which we're going to call E, the vector. This is eccentricity. And you might be thinking to yourself, I'm familiar with eccentricity. I've heard that before. It is, first of all, is constant. But I've seen eccentricity before as a scalar value, not as a vector value. So you might be familiar with, let's say you've got some central massive body here, and then you've got some circular orbits, as best as I can draw a circle. I'll take it. It's decent. And for a circular orbit, we know that E is 0. And then we know that, let's say you increase eccentricity, and maybe this is E is between 0 and 1. That would be an elliptical orbit. And then imagine, actually, you know what? Let's do this. You know what? Let's do some real justice to this. I can actually color code this diagram. This is about to look really cool. Well, maybe not. It's about to look as good as I can draw it. So let's say you've got your central massive body here. And then that's a circle. Maybe I should have just started with some head and then erased all the other features, but that's my best circle. So this is the E equals 0 or circular orbit case. Now, let's see, what other markers can I use? Let's do maybe orange. Let's see how orange looks. So then from here, I'm going to keep 1 point in common. If we, oh, I can do better than that. If you take the far point and drag it out, you get, when E is between 0 and 1, you've got an elliptical orbit. And that's most of where we're going to be spending time in our class, is an elliptical orbit. Now, let's say that green case here. Imagine you've got this far point, and you just move it further and further and further away without changing the near point. In the extreme, you'll get some shape that does this. And at that point, E is equal to 1. Your furthest point is actually infinitely far away. That is the definition of a parabola, like from algebra class. So this would be a parabolic orbit. And then finally, if we take it even further, we'll do blue. You take it even past a parabola, now it's almost like the furthest point is infinitely far away in some negative direction, if that were to make sense. And so you're kind of even more extreme. This would be, think about like a flyby maneuver, right? It's like you come screaming in from infinity and screaming off to infinity, and you don't stay in orbit of the body, but your trajectory is affected by that body. Whenever E is in excess of 1, this is a hyperbola or a hyperbolic orbit. So below a parabola, these are called closed orbits. And then above a parabola, this is an open orbit. So you could think of it like, are you eventually going to come back to your starting point? Yes. Well, then it's either a circle or an ellipse. And then are you not? Are you going to fly off to infinity? Then it's either a parabola or a hyperbola. We're going to spend most of our time, almost all of our time, on the elliptical case, and then the remainder of our time on the hyperbolic case. We're not going to talk nearly as much about circles or parabolas, because circles are really just a special type of ellipse, and then parabola is just a special type of hyperbola, in the same way that like a square is a special type of rectangle. Same idea. Now here's what's really cool. this point of closest approach, if you were to draw a vector from the central massive body out through that point of closest approach, that's E. So what's neat is the magnitude of E tells you about the shape of the orbit. The direction of E tells you where in space the point of closest approach is. So I think that's pretty nifty. And we will absolutely be using eccentricity in our future work. So questions on orbital eccentricity, or did that track reasonably well? All right, cool stuff. Next, we'll take a break in a minute, but first I'm just going to go through and vomit a bunch of useful equations at you without derivation. So useful equations. All right. So the first of these is for any, or let's start with a picture probably. That'd be a good place to start. Let's say that you've got some central massive body here, and let's say that you've got an orbit of that massive body. Now I'm going to try do my best to make this symmetrical here. That's reasonably good. And let's set, this is the ellipse in question. This is the central massive body, which is at some focal point F. But then there's also some focal point floating out in space, which we'll call F prime, which doesn't have any center of mass at it. The center of mass is at F. Okay. Let's call this point here P, point of closest approach. And this is the eccentricity vector E. There's also some point out here A, which is the point of furthest distance. Okay. Now, this distance here is the shorter of the two axes. So it's a little bit like the radius of a circle. But of course, an ellipse has two radii. So you could think of them as the major and the minor radii. Or in this case, this B is the semi-minor axis, and this A is the semi-major axis, if that makes sense. And then similarly, if we draw a dotted line down here, this distance is the distance scalar corresponding to closest approach, and this distance scalar is the distance corresponding to the furthest that you'll be away from the center of that body. Hopefully that all makes sense. Okay, so even before we name the terms in question, hopefully you can see that this distance RA and this distance RP added together is the semi-major axis times 2, which would just be the full major axis, so 2A. Or similarly, you can think of A as the average of those two distances. So we can start with that equation, but before we get there, we're going to name these terms. P, the point of closest approach, is referred to as periapsis. Now, in the case of an Earth orbit, it's sometimes called perigee. In the case of a lunar orbit, it's perilune. So the suffix depends on the body that you're working with. Apsis is the generic one. So you're never going to sound like an idiot saying periapsis. But if you talk about the perigee of a lunar orbit, then people are going to think you're being silly. If you're orbiting the sun, it's perihelion. And if you want to sound really cool at parties, you can name them for all the planets. I like, for Mars, it's periarion, which I think is kind of neat. The point of farthest approach, or the furthest you'll get away from the central massive body, is apoapsis, or apogee, or apolune, or aphelion. You get the idea. And so hopefully it's clear from this diagram that RA plus RP is equal to 2A. Right. Now, here's what's neat. you can also say, okay, let's say that the body in question at this instant in time is at some point on its orbit such that the angle between perigee and it is some angle theta. And it's got some distance from the central massive body, r, where r is just the norm of the vector r, if that makes sense. Well, we can compute r as a function of theta by this equation. H squared, scalar h, over mu 1 plus e cosine theta. And then similarly, you can invert this. Hopefully this makes sense. H is the specific angular momentum. Mu is the gravitational parameter of the central massive body. E is the eccentricity, and then cosine of theta. You can also say, if you invert this equation, that theta is the negative arc cosine of h squared minus r mu over r mu. I don't recommend it because this equation is wrong 50% of the time. Because there is ambiguity about what quadrant you're in, right? Whenever you do an arc cosine, remember that a negative angle and a positive angle will give you the same arc cosine result. So you must do a quadrant check. What I tend to prefer is if you've got the full position vector, you can compute theta using an arctangent. You can imagine you've got the x component and the y component of the position. Arctangent gets you there. That's my preferred method. You can also take some shortcuts here. RT is just h squared over mu 1 plus e, which makes sense. If theta is 0, cosine of theta is 1. Now, if theta is 180 degrees, then cosine of theta is -1. So hopefully it makes sense that RA is h squared over mu 1 minus e. All right, so far so good. The next bit we're going to talk about is velocity. Oh, and while we're at it, sorry, I'm kind of, my eyes are glancing around the page and I'm like, let's talk about this now. RP is also semi-major axis times 1 minus e. And RA is also the semi-major axis times 1 plus e. So you can use that equation as well. Like I said, presented without derivation. I'm just going to drop these equations in your lab. Here's a really useful one. The specific angular momentum squared is a mu 1 minus e squared. So there's the relationship between a and h squared. And then hopefully this makes sense too. The not the semi-major axis, the eccentricity E is RA minus RP over RA plus RP. So I'm basically just dumping a crib sheet on you at this point. Similarly, what else can we do? Let's talk about velocity here, and then we'll take a break. So let's zoom in on this diagram here. Let's say that we're still on an elliptical orbit. We're just zooming in. This is the, theta or E? Oh, whoops. It makes perfect sense to me. No, I'm just kidding. All right. E. Yep, hopefully that makes sense. Okay, cool. So let's say that you've got some point here, and it's got some position, and it's got some velocity. Well, I'd also like to introduce a new reference frame, which I'm going to call the orbital reference frame. Now, the orbital reference frame has one vector, the ER direction, pointing along the radial vector, and then the other one, E tangential or E theta, pointing in the direction of increasing theta. Now, as drawn, v is entirely in the e theta direction, but that's not entirely true, right? Imagine for a circular orbit, your velocity is always going to be perpendicular to your position. But for an elliptical orbit, there will be moments where you're getting closer to the body and getting further away from the body. So in this case, and just to remind everybody, this is still the eccentricity vector. Right. We can come up with equations for the component of velocity in the radial direction, your radial velocity, and the component of your velocity in the tangential direction. So radial velocity and tangential velocity. Okay. Radial velocity is v r, which is equal to mu over h e sine theta. And then we're going to call this v theta is mu over h 1 plus e cosine theta. So that gives you radial and tangential velocity. And what else? Oh, the last little bit here, at least I'm looking at my crib sheet. I think this is everything you need for now, is the period of an elliptical orbit. We're going to call that period tau. So the time it takes for a point, a spacecraft to orbit all the way back to its original position. Tau is 2 pi semi-major axis to the 3/2 power over the square root of mu. Sorry, tried to make that look good. And again, just dropping that in here without derivation. And that's about it for now. I think that's everything we need. Again, in a proper orbital mechanics class, you would go over this information over the course of multiple lectures, and you would make each of it make sense. A lot of this just comes from geometry, but for now, I'm just going to kind of vomit this crib sheet at you and then call it a day. So let's pause for now. It's the top of the hour. If you want to ask any questions, go for it. Otherwise, let's come back at 7:01. Sorry, it's 7:01 now. 6:01 for me. 7:11. And then we'll talk about Kepler's equations.
I had a quick question just to make sure I'm not being dumb. E is
Sure.
the magnitude of the eccentricity vector, right?
Yes. Yep.
Okay. Thank you.
Yep, absolutely. All right, time to start back up. So we're going to finish up today by talking about Kepler's law, and then numerical example of Kepler's law. So I'm curious, is anybody familiar with Kepler's law already or has worked with this? Maybe if you've taken orbital mechanics. When I say the name Kepler, what comes to mind? Oh, you can just turn on your mic. Nope, maybe not. Thought I saw a hand up. Or if you want to type something in the chat, that's good too.
Isn't it something about the area of between like a focal point?
Yeah, absolutely.
Spots?
So here is the fanciness. So there's some really cool stories about kind of the history of orbital mechanics, and people were kind of staring at things orbiting for a long, long time and crunching numbers for a long, long time. And Kepler noticed something that was absolutely bananas, which is that let's say you've got some wedge here with some area here. So let's call this area A1. And let's say that the spacecraft starts here at some time T1, and then later at some time T2, it's here. Right? Well, then here's what's nuts. Oh, hang on. Is that over here, oh, I can do better than that. Marginally better, at least. Over here, let's call this A2, and we'll call this T3 and T4. So you might be familiar, if you've seen animations of something in orbit, that the further away the orbiting body gets from the central massive body, it tends to slow down. And then when it gets closer, it tends to speed back up again. But what Kepler noticed is that if A1 equals A2, then T2 minus T1 is equal to T4 minus T3. Or in other words, an orbiting body sweeps out equal areas of the ellipse in equal time. It's not equal distances in equal time, but it's equal areas in equal time. Hopefully that makes sense. Now, this is tremendous. This has very far-reaching implications, and it's extremely useful. Kepler's equations are used all the time, even today. And so what Kepler came up with, or what we've kind of come up with as a result of Kepler's work, is if we want to be able to explain the state of a spacecraft or any orbiting body at some future time, we need some equation, which all these other equations that we've gone through today are nice. They are not functions of time. We need something that's a function of time. So we want to write theta as a function of time for an elliptical orbit. Okay? But theta dot is not constant. Right? So you see how if the velocity is always changing and the position is always changing, it gets really complicated trying to say something like, okay, right now, the angle between you know, periapsis and the spacecraft is 15 degrees, how long is it going to take for it to be 30 degrees? It gets really tricky to answer questions like that for an elliptical orbit. Now, for a circular orbit, this is so easy because it's constant, right? Your velocity is constant for a circular orbit. So for a circular orbit, we could just say this. Your velocity, which is r theta dot squared. You know what? Let's just do it this way. All right. R theta dot squared is mu over r squared, or you could say that theta dot circ, which is a constant value, is mu over r cubed, right, for a circular orbit. I think we actually derived that on the first day. I have to go back through our old notes, did we? Oh, sorry, v is square root of mu over r. We're talking about theta dot, so it's a little bit different. But you get the idea here. Theta dot is a constant for a circular orbit. So our strategy is this. Turn a hard problem into an easy problem. We're going to map an orbit ellipse to some made-up circle. Do the analysis there. And map back. Okay, so here come circles that I don't screw up. Let's see how this goes. So let's say here, okay, not terrible. And let's say we've got an orbiting body, which is on this extremely elliptical orbit. And then let's just project this up into a perfect circle. So imagine you took the top and the bottom and you just kind of tugged them up. So this outer one is a circle, the inner one is an ellipse. And then later, I'm going to need this again. This is that perfect circle again. Okay, so let's say, and let's take this as our midpoint here. Let's say that this is the focus of the ellipse. And let's say that at some instant in time, the orbiting body or the spacecraft in question is up here. Okay. Now, if we were to take this point and then just kind of stretch it up vertically, it would be here. And if we draw a vector up to that point, it would look like this. Okay. So what I'm saying is, if this angle here, which we'll call theta, this can be related to some other angle, which we'll call E. Okay. Where theta is called true anomaly. So that is the angle between the eccentricity vector and the vector to your spacecraft. So you could think of theta as kind of the clocking angle, right? That's always changing. E is your eccentric anomaly. Okay. So it's a little bit like, it's not like, but it's a little bit like, if you're familiar with Laplace transforms, we take a hard math problem, we do a Laplace transform to it, it becomes easy, and then we un-Laplace it. It's a little bit like that. We're going to relate theta to E, and then we're going to do all of our work on E, and then we relate E back to theta. That's the idea. Theta is the one that kind of makes sense to us. E is a little bit made up. Okay. So now this area that has been swept out, yep, we're thinking about sweeping out equal areas in equal time. We're going to call this area, well, it's actually equal to A. We're going to call it AE. This is the eccentric area. Okay. Now, this distance here is going to be semi-major axis times the cosine of E. Hopefully that makes sense. But then this distance here, if this vector is r, is going to be r times the cosine of theta. Okay. And so if you were to take this problem and stretch it up, so here's the same point here, the same focal point. This is the same midpoint of the circle. We're just ditching the ellipse for now. Hopefully this makes a little bit more sense. Right. Here is this same point from before. Here is the same angle E. But now we're going to stretch up this vector. So it goes this way. Hopefully this makes sense. All we've done is take this ellipse and stretch it up to meet the circle. What we end up with is some AC, some circular area. It's the same shaded region. I hope that's clear. We've just stretched it. Now this distance is semi-major axis times E. And then this distance is perigee radius. Okay. And then this distance here is A. Okay. So once this all makes sense, we're going to start using some fun math tricks and hopefully making things get real simple real quick. So the first is that the circular area is just the scaled version of the elliptical area, and the scale factor is B over A. That makes sense. Where B is the semi-minor axis, A is the semi-major axis. Oh, sorry, other way around. Oops, A over B. That should make sense, hopefully, because A should be larger than B. Circular area is larger than the elliptical area. Similarly, we know that the derivative of the elliptical area with respect to time, A, E dot, is constant. Right? Isn't that what we just said? That the area that's swept out is an equal area over equal times. So you could think of this as having a constant derivative. All right. Now, what we'd like to say is AC is the area of a wedge minus the area of a triangle. Right? So I'm going to use colors for a minute, and then I'm going to erase it because this is going to get real confusing. If we wanted to compute AC, right? AC, yeah, immediately, like this is going to get ugly, is this wedge minus this triangle. Hopefully that makes sense. So AC is the red triangle, sorry, the red wedge minus the blue triangle. So let's focus on the wedge first. So the wedge is just going to be, let's see here, 1/2. Do I have this right? Okay, yes. 1/2 A squared. E is the area of the wedge, and then the triangle is 1/2 base times height is 1/2 times A times E multiplied by A sine of E. Okay, So where AE is this base, and then the height is A sine E. And this gives us 1/2 A squared E minus E sine E. Already, this is starting to look a little bit familiar if you've seen Kepler's equation before. Now, the elliptical area here is just the scaled form of the circular area, right? Isn't it just B over A times the circular area? Which you could also say is 1/2 A B E minus E sine E. Okay. Now we said before that the d dt AE is constant, and that's equal to the area of the ellipse divided by the orbit period. That is a constant value. And the area of the ellipse is pi. It would be pi r squared if it was a circle. It's pi semi-major axis, semi-minor axis for an ellipse. And then the orbit period is 2 pi square root of A cubed over mu. Cancel, cancel. Okay, so dA dt is AB over 2 square root of A cubed over mu. So it's about to get a little ugly here. What we'd like to say then is, if this is divided by square root of A cubed over mu, then you could say that this is AB over 2 times the square root of mu over A cubed. Just simplifies things a tiny bit. All right. So next, we say, okay, if dA dt is this, then dA is AB over 2 square root of mu over A cubed dt. Okay, time for some fun calculus tricks here. So you can actually take the integral of both sides, and you can say that AE is, okay, we're integrating with respect to time. AB over 2 square root mu over A cubed does not have time in it. So actually all of this is just a constant. So it's AB over 2 square root of mu over A cubed, integral from some initial time to some final time, dt, which is just A B square root of mu over A cubed, and then just the time since the initial time, if that makes sense. All right, so now we said that this is AE, okay, but then AE is B over A times AC, remember? So we've got this term, I'm going to color code. This term is this term, and then this term is this term. So we're going to relate those. And when we do that, we get AB over 2 square root of mu over A cubed T minus T naught is equal to B over A times 1/2 times A squared E minus E sine E. Okay, let's simplify a few things here. So this a cancels with this a squared. This b cancels with this b. And let's see what else. This a cancels with this a. And this 2 cancels with this 2. Oh, things are getting a lot simpler here. And so what we find, and I'm actually going to switch the order here just to make this a little bit more familiar, is E minus E sine E is equal to square root of mu over a cubed t minus t naught. Okay. Where a couple of different things. First of all, this is the solution. This is Kepler's equation. Profoundly useful equation, which allows us to relate a change in time to a change in eccentric anomaly. Okay. Now, I need to explain a few things though. First of all, t minus t naught, I think of this as time since periapsis. Right. Where in this case, the start time between, you can think of it as like right here to right here is what defines this area. You need to start from periapsis. So Kepler's equation does not work for any given t1 and t2. It works for time since periapsis. That's an important distinction. Also, the entire right-hand side of this equation is sometimes written as m, or mean anomaly. Just in case you see that written down somewhere, that's what mean anomaly is. All right, so you can also go through, and again, this is going to be frustrating, left as an exercise to the reader and presented without derivation. I'm also going to give you the other equation. And hopefully you can go through, if you really want to, and make this make sense using just geometry and trigonometry. The relationship between theta and E is this. Tangent of theta over 2 is 1 plus E, 1 minus E square root, tangent of E over 2. So again, going back to the idea of Laplace transforms, right? Laplace transforms allow us to take a differential equation, and then we kind of go to Narnia with it. And in this other world, the math problem is a lot easier to solve, and then we go back again at the end. So you could say, use this equation to go from theta to E, and then use this equation to map E forward in time or backwards in time. And then once you've got the new E as a function of time or time as a function of E, you can go back to theta. That's the idea. All right. Now, also presented without derivation, just in case this is helpful to you, is for hyperbolic orbits. I don't think we'll need in this class, but just in case, the equations look a little bit different. This is mu over a cubed t minus t naught, which is still time since periapsis, is equal to E hyperbolic sine, which is not the same thing as sine, of f minus f, where f is kind of the equivalent of eccentric anomaly in this case. And then you can also say that the tangent of theta over 2 is equal to the square root of E plus 1, E minus 1, hyperbolic tangent, which is not the same thing as tangent, of f over 2. So those are useful for hyperbolic orbits. We're going to be focusing on the red equations. And so you can imagine that this would allow you to solve for time since periapsis as a function of true anomaly, or true anomaly as a function of time since periapsis. Super duper useful. I want to go through a quick example and make it clear that this is not without its hiccups, its shortcomings. So basically, this gives us a math problem which is really easy to solve one way and then almost impossible to solve the other way. But really quick, I want to pause here. Questions on Kepler's law? Good stuff. Okay. Want to do 2 examples and then I'll let everybody go. And the rest of this is numerical examples. So if you have a massive time crunching and need to get out of here, we're done going through new content. The rest of this is just examples. So I'm going to borrow undergraduate spaceflight mechanics textbook, the Howard Curtis orbital mechanics book. I want to take example 3.1 and 3.2 from that book and just show you something really quick. So this is an example solving Kepler for time. I want to show you how easy this is. Okay. So imagine you've got, here's the Earth, and you've got orbit of the Earth. Okay. And let's say that at some moment in time, we've got some theta, some r. Here's the point. And this is our point of apogee, and this is our point of perigee. RA, RP. Okay, so all I'm going to say is theta is 120 degrees. And what else? RP is 9,600 kilometers. And RA is 21,000 kilometers. And we're going to say solve for time since periapsis. I'm going to write this as T minus TP. Right? So what we're doing is finding the time from perigee to theta is 120 degrees. All right. And what we will need, first of all, do not work in degrees when using Kepler's equations. Why is that? I don't have a problem with degrees. I think degrees is fine. You'll notice the equation is E minus E sine E. So E, an angle, minus the sine of an angle. What we have here is a naked angle. It is an angle that you are not doing a trig function to. That has to be in radians. Otherwise, this whole equation falls apart. If you try to plug 120 degrees in for theta and then leave it in degrees, you're going to have a bad time. We need to work in radians. So just wanted to make that point. In order to proceed, so we will need E, A, and E to solve. All right. E, if we just scroll up, is RA minus RP over RA plus RP. And if you plug in and solve, you get that E is 0.37225. And semi-major axis is just the average of radius of perigee and radius of apogee, which works out to be 15,300 kilometers. Okay. Now, if we want E, then we'll need to take this equation here and solve it for E. E works out to be 2 tangent inverse of square root of 1 minus E, 1 plus E, tangent of theta over 2. Sorry, we'll do squiggly bracket here. And E is 1.7281 radians. And I give you the numbers in case you want to go through and code this up on your own. Okay. Well, then in this case, we just solve Kepler's equation. Okay. We have E sine E, we have mu and A cubed. So all we would need to do is say T minus TP, and I use that interchangeably with T minus T0, Well, that's just the square root of a cubed over mu times e minus e sine of e. And if you go through and solve it, you get 4,077 seconds, which you can do a sanity check. That ought to be less than half the orbit period, probably less than quarter of the orbit period. So hopefully that makes some sense. Now, if I had asked, so now, what about solving for the time from theta 1 is 120 degrees to theta 2 is 130 degrees. You cannot take the difference of those and plug in 10 degrees. That's not how that works. Kepler's equation will only find you the time from perigee to your current true anomaly. It will not find you the time between two true anomalies. So you would need to solve for T1 given theta 1, and then solve for T2 given theta 2, and then subtract. Right? There's no shortcuts. Right. Now, this is the easy one. It gets a lot worse. So I want to do one other quick. The next example is solving Kepler the other way. So this is almost like, you know how a diode in a circuit only lets the current go one way, or like, you know, the little sharp barbs they have in traffic only let your car drive over it the one way and not the other. Kepler is like skiing down a mountain the one way, and it's like climbing a mountain the other way. And it has to do with just a numerical solution problem. So if we take same orbit, we try to solve it the other way. So solving Kepler for true anomaly. And this will be on the homework. For the orbit from the previous example, find theta when t minus tp, or time since periapsis, is 3 hours, or 10,800 seconds. Okay. So let's look at Kepler's equation then. So E minus E sine E is square root mu over A cubed T minus T naught. So we have T minus T naught. Right? What we want is E. This gets pretty bad pretty quickly. So E minus E sine E is square root mu over A cubed T minus TP, which we can solve. We know mu, we know A, we know T minus TP. The whole right-hand side of the equation is 3.6029 radians. Okay? So if we plug some numbers in, capital E minus 0.37225 sine of E equals 3.6029. Solve for E. And here's the problem. There is no analytical solution for E. There's no way to move things around using algebra to get E alone on one side of the equation. The only thing we can do is guess and check. And this is where the problem is, right? There are many, I'm pretty sure it's still a field of ongoing research. Like I've seen relatively recent papers on like more modern solutions to Kepler's problem. But what it basically boils down to is we guess and check. We use some sort of a nonlinear solver, numerical technique. So I'm going to leave this as an exercise to the reader. There are MATLAB functions which can allow you to solve a nonlinear problem like this with an initial guess. I'm going to say solve for E, use numerical techniques. And this is left as an exercise to the reader. But when we're done, we get that E is 3.4794 radians. And then it's easy, right? We could just say theta is 2 tangent inverse square root 1 plus E over 1 minus E tangent of E over 2. And we can solve this, and we get negative 2.912 radians, which is the same as 3.371 radians, right? Add 2 pi, which works out to be about 193.16 degrees. So you can put your final answer in degrees, but you need to work in radians for the rest of the problem. Okay, so you see the issue here. If you want to solve Kepler for true anomaly, you need to use some nonlinear solution scheme. But if you want to solve it for time, it's the simplest thing in the world. Both of these are on your homework. So what I recommend is, as kind of a warm-up exercise to homework 1, I would go through and try to demonstrate that you can solve these for yourself in either MATLAB or Python. But that's pretty much it. So I think that is enough for now. I think I've kept you late enough. I'm going to post homework 1 tonight. You can start taking a look at it, or after class next time, we're going to spend a while kind of talking about it. But that's about it. So unless anybody has any questions,